Let's now go ahead and try yet another estimator object. Recall that we started this process with the simplest kind of estimator, that was a linear regressor. We then went ahead and used a more powerful one, that was a DNN regressor. In a DNN regressor, all of our features were passed through a deep neural network. As we've discussed in previous portions of this class, deep neural networks do not always make sense for all kinds of features. For more sparse features, a wide neural network might work better. So let's go ahead and try something which hopefully will give us the best of both worlds. Let's go and try a linear combined regressor instead. A linear combined regressor is a pretty interesting type of model. This effectively combines two neural networks, one of which is deep and the other of which is wide. And for this reason, a model of this sort is called a deep and wide model. Let's very quickly take a look at what the TensorFlow docs have to say about deep, wide, and deep and wide models. We can see in the topologies right up top that at one extreme we have very wide models which have a large number of features but a relatively small number of layers. At the other extreme we have deep models where we have a relatively small number of features but many feed forward layers. And in between is the wide and deep model. Notice here how there are hidden layers and dense embeddings. These correspond to the deep features. There are also some wide features which are going to be fed directly from the output without passing through any of the hidden layers. If we read the text below, it really talks about how there are just three steps if we want to configure and use a wide and deep model using the TensorFlow Estimator API. In the first step, we've got to select features for the wide part. That is something that we've already done. These are the sparse base columns and the crossed columns. So this portion is already done. The next bit is to select features for the deep part. And these will be the continuous columns. These are embedded dimensions, more on embeddings in just a moment. And the last step is to combine all of them into a wide and deep model. As you might expect, that last step is really pretty simple. We simply instantiate a different kind of model object. This time we instantiate a DNN linear combined regressor. This highlighted bit of code that you see on screen now is the culmination of this process. Notice how in this instantiation, we specify linear features. Those are the white columns. We also specify some deep columns. That's for the deep part of the neural network. And we also need to specify an array which has the list of neurons that we want in each of the layers of our hidden neural network. We've already done the heavy lifting of setting up all of our features for both the deep and the wide columns. Let's now just arrange them in exactly the format which is required for instantiating this estimator object. The wide columns include our pickup and drop off locations, the crossed columns for the pairs of the pickup and drop off, as well as the day of the week, as well as the time of the day. And finally, we also include in there the passenger count because that has a linear relationship. That's what we expect with the fare. That does it for the wide columns. Let's now turn our attention to the deep columns. This introduces a new type of layer which we've not seen so far, that is a layers.embedding column. This is something that we would use when we have sparse high dimensional features and we want to convert them into dense low dimensional ones. What does this term high dimensional represent here? Well, if we look at our pair of pairs, that is a crossed column of crossed columns, that is going to have a pretty high dimensionality because that is one feature which has four dimensions. Those four dimensions are the pickup latitude, the pickup longitude, the drop off latitude, and the drop off longitude. So that is a perfect case for us to use an embedding column. That's the PD pair. We also have another high dimensional feature, that is the day and the hour, that has a dimensionality of 2. And that's why we have two layers of type embedding column. That's because we had two features of dimensionality greater than 1. The other deep columns include all of our real valued columns as before. Let's very quickly glance at what the docs have to say about embeddings. As we've already discussed, these make sense within the deep portion of our wide and deep model. The deep model within that wide and deep model is a traditional feed forward neural network, and it's going to expect data which is low dimensionality and very dense. So if we have any columns which are sparse and high dimensional, we are going to use the embedding column in order to convert them from sparse high dimensional data into dense low dimensional data. And now we are done. We can go ahead and instantiate our DNN linear combined regressor object. As before, we specify a model directory. We've already discussed this line of code in some detail. We need to separately specify the deep features, the wide features, as well as the number of neurons in each of the layers of the deep portion of our model. Let's now go ahead and add one last engineered feature. This engineered feature is simply going to consist of the Euclidean distance between the pickup and the drop off point. In order to calculate this distance, we first subtract the latitudes and longitudes of the pickup and the drop off, and then we compute the sum of the squares of those distances. This is the same distance formula that we probably learned in high school coordinate geometry, and this gives us the Euclidean distance, which corresponds to the trip length, or at least is a reasonable approximation for that trip length. We are almost at the end of this detailed look at the code for our deep and wide model. One last bit worth paying attention to is this serving input function. Notice how the return value from our serving input function is of a specific type. It is of type input function utils dot input function ops. And in case you're wondering what that's all about, that's just a way of enforcing some type safety on the serving input function. Let's also very quickly recall what the serving input function is in the first place. Remember that while using estimators, after instantiating the estimator, we invoke the fit method. This fit method needs to be passed in a function. This is a function which will tell that fit method of the model estimator how to get the training data or the validation data. Such a function needs to have a specific return type. That return type needs to be a tuple of features comma label. The features need to be also in the form of a dictionary. The labels need to be simply a list of the y values. After invoking fit on an estimator object, we then use that estimator object for actual prediction. This is the trained object which we are now using for prediction, and the predict method also requires an input function. This input function should tell the model where to get the prediction data from, the x values which have to be used to output the y prediction. This function once again needs to have a specific form. It should only return the features. Clearly, we do not have a label available during prediction. We do have labels available during training. This function object, which you now see on screen, this is the serving input function, and this better conform to a particular type, and that type is the input function ops. As the docs of TensorFlow tell us, the input function ops is used to enforce some kind of type safety. We should use this only for the serving input function, where we specify that the features are going to be dictionaries, where the keys are going to be the feature names, and the values are going to be the tensors corresponding to the actual X data. Because this is a serving input function, the labels need to be set to none. And that is exactly how we make use of the input function ops as the return value of our serving input function. One last bit worth calling out here is the fact that we call the add engineered method. This is in the return value. This add engineered method has the effect of adding the Euclidean distance feature which we just calculated. We also need to make sure that we are invoking this add engineered features method in the training function as well. This is in the input functions which are going to be used in the training and validation phases. So we've got to tweak the last line of the input functions for those phases of our model building as well. With this, we are now done. We can go ahead and actually train our model and then use it for prediction. So that's coming up next.